I'm Henry. I'm a PhD student at Stanford, and I'm going to talk about, again, privacy-preserving computation of aggregate statistics. So I think most of us probably have tons of devices running on our mobile phones, and a really common thing that providers of these applications want to do is compute aggregate statistics over their entire user population. So you can imagine having a stress tracker app, say, installed on your phone, and the provider of this application might want to know the relationship between its users' blood pressure and its users', say, Twitter habits. So sort of each user of the application has a private data point stored on its phone with, say, its blood pressure and it's like how many hours a day you're on Twitter. And the provider of this app wants to sort of fit a line to these points. You know, say it has 1 million users, it wants to draw a line through these 1 million points. So the way this works today is with what I'll call non-private aggregation, where your phone just sends your data up to some server controlled by the app, and the app provider basically fits the line on its own in the clear, like over the data in the clear. So this is good in that it gets the right answer, but it's bad in that the app provider learned way more about you than it wanted to, right? It just wanted this line of best fit, but instead it got everybody's private data, which, as we heard before, is sort of causes legal problems, regulatory problems, privacy problems, lots of problems. So this work is about sort of how you do this in a privacy-preserving way, one way of doing this in a privacy-preserving way. And we're building on sort of MPC-like techniques. So the clients will now sort of, instead of sending their data to the server in the clear, they'll split their data into pieces using a secret sharing scheme and send one piece of their data to multiple servers. So you can think about, say, Google's App Store running one server and the app provider running a second server. So neither server sees your data in the clear, and yet somehow they're able to compute the aggregate statistic of interest. They're able to compute, say, the line of best fit, and they don't learn anything else. So this is where we're going. To define the problem with a little bit more precision, you can think of sort of having 1 million phones, say, and each phone has a private data point xi. And we have some number of servers that want to compute some interesting function over all the xi's. And whatever system we come up with needs to satisfy a bunch of sort of goodness notions. So we'd like it to be exactly correct in the sense that if the servers do the right thing, they get the right answer. It should be private in a cryptographic sense in that if at least one of the servers does the right thing, this aggregation function on the data is the only thing that servers learn. They don't learn anything else. The third property, which may not be as obvious, is that you'd like sort of malicious clients to not be able to screw up the system too badly. So to explain what I mean by that, you can imagine of one bad client submitting a data point that's way off the charts in an attempt to sort of skew the aggregate statistic that you compute, right? And you'd somehow like to say that this doesn't happen. The reason this can be problematic is because the servers never actually see the data points in the clear. So unless you can defend against this, the servers might compute totally the wrong aggregate and have no idea that this sort of attack has occurred. So that's what I mean when I say robustness. And then for practical reasons, we'd like this to be really efficient in the sense of we don't have to use lots of public key crypto. So think about information theoretic crypto only. And the system called PRIO that we've built, just sort of designed and built, is the first system for private aggregation that I know of that achieves all 4 of these properties at the same time. And I'm not going to talk about it so much today, but it supports a pretty wide range of aggregation functions of interest. So sort of the contributions of this work that we've done are 2. The first is a new technique for defending against malicious clients very efficiently. And we call this technique secret shared non-interactive proofs. And the basic idea is that the client can prove to these servers that what it's submitting is sort of a well-formed request or well-formed submission without leaking to the servers what the submission actually is. And the observation is that in this setting where you have multiple non-colluding servers, you can do things much more efficiently than you can in sort of traditional crypto settings where you need zero-knowledge proofs, for example. The second contribution I'm not going to talk about, but are sort of ways to go from a system that can compute sums privately to a system that computes many more interesting functions privately, like linear regression or other things. So there's a bunch of different ways to do private aggregation. There's tons of related work that I won't have time to talk about. I'll just say that sort of if you look at the way we've defined these 4 properties, and there's which we've sort of picked because they seem relevant to practice, I don't think any of these prior systems achieve these 4. They achieve different things, which are also interesting. But sort of the differentiating point for us was being able to get sort of exact answers, cryptographic notion of privacy, and also defend against malicious clients without killing the performance of the system. Any questions about this so far? Yeah.
To what extent is robustness a property of the protocol versus a property of the function you're computing?
So what I mean by robustness is we should have some notion of validity of a data point. And
okay,
yeah.
But that's not like a protocol level, right? Like you can't specify that without. To what extent is that like specific to your system, or is that just like, you know, robust statistics, for example, is like
sure.
You know, a well-established field.
Yes.
Why do you need your own solution to this?
So you can sort of jam the robustness into the function, but then so you can imagine defining a function that sort of rejects all of the invalid inputs and then outputs whatever it's supposed to output. You could do that, but it turns out then you can't you can't implement that in an MPC in an efficient way for the most part. So yeah, you're right. There's some sort of you sort of have to at some point. So what we do at some point is sort of define a notion of valid data points and then define a simple function over those valid data points. You could define a complicated function over all data points, but somehow that is difficult to implement. But yeah, it's a good point that if your function is sort of inherently robust to outliers, then and you can implement that in an MPC, then that's another way to do it.
I guess even if you're doing validity checks where you're rejecting outliers, you know, at that level, it just seems like you're mixing layers of abstraction in your specification of the problem.
I see. Well, I mean, I guess if you are willing to entertain that sort of averages are interesting, like the averaging function is a good function to compute. It seems natural, at least to me, to sort of define averaging where the inputs to your averaging function have a certain sort of you want to check that they satisfy some predicate ahead of time. But yeah, I totally agree that if maybe this is the wrong notion, and you could look at a different notion that would be more natural. Yeah.
So just to clarify the model, you have a very large number of devices submitting examples, and then you're assuming kind of some smaller set of non-colluding servers that are running the protocol.
Right.
But more than one.
Correct. Anything else? Yeah.
So just to clarify, so given the function that you want to compute, you have a way to decide if the point is influential or not. That's what you mean by validity of the point. And then you proceed to compute your function. I mean, you remove the point if you believe it's influential, and you proceed to compute the function.
Sure. Right. So the definition of influential or not is up to the person deploying the system. So they can use whatever that. So they can say a blood pressure reading less than 200 is appropriate, or they can say it's less than 180. But that's sort of, they can define whatever predicate they want on a data point, and that's the predicate that we will check.
But that is what you just said. It's a little bit different from what I'm asking, because I think in statistics, typically the way you define an influential point is given the function that you want to compute.
Right.
And you have just specified something that is agnostic to the function that you're computing.
Correct. Right. The notion of validity is independent of the properties of the function.
And so is the notion of validity also independent of the rest of the data set? Is it the property of a single data point?
Yes.
I see. Okay. All right. So it's just a filter on.
Exactly. Yeah.
Right. And like, why is that different from just saying, okay, the domain of the function is, you know, numbers between 0 and 1. Vector is not bigger than this norm. It just, there's something a little like.
Sure.
I'm just sort of confused of why it's specified as a property of the system as opposed to sort of a property of the computation you want to perform.
Sure. I think you could define it that way. I guess in the world of MPC, where you're sort of always operating over finite fields of a particular size, it's natural. It's sort of hard to constrain the domain of your function without sort of making the MPC way more difficult. So I guess in the world of MPC, where everything is always sort of finite field elements, it's nice to be able to say, okay, this tuple of finite field elements is valid if, you know, it represents a location or it represents latitude and longitude, and those like lie on the Earth in some range, even though the field is going to be much bigger than the valid range. But yeah, I totally agree that there may be more natural ways to do this. Yeah.
Yeah. Go ahead.
Cool. Okay, so let me give sort of, I'll blow through this pretty quickly. This is sort of the strawman solution for computing private sums. Then I'll talk about sort of how we check validity in the sense or provide robustness. If I have time, I'll talk about evaluation results, and then at the very end, talk about sort of what we hear from people who think about deploying these things in practice, whether or not they're practical. So as a sort of toy example, imagine a setting in which every device, again, think of a phone, has a value xi, and we want to compute just the sum of the xi's. So this is sort of the simplest example. So as a toy application, you can think of sort of having your location be 1 if you're on the Bay Bridge, your xi is 1 if you're on the Bay Bridge, and 0 otherwise. And then the sum of the xi's just tells you how many people are on the Bay Bridge. Okay, so this is sort of the simplest MPC-like scheme you can talk about. So the way this will work, at least a straw man scheme that's sort of building up to what we actually do, is you have some number of servers, and I'm going to assume that the servers are non-colluding, or at least one of the servers is honest. So think of sort of the App Store, again, as running one server, an app provider is running a second server, or maybe 3 different governments running 3 different servers. However you get them, you need at least one of the servers to be honest. So the way clients interact with the system is sort of a client comes online, it has its private data point. So this client is on the Bay Bridge, and it splits its value using a cryptographic secret sharing scheme. So it just picks 3 random numbers that sum to its private value. And I assume most of you have seen secret sharing before, but the basic idea is you need all the shares to recover the private value. Okay, so if you only see 2 out of the 3 shares, you don't learn anything about the client's data. So the client sort of splits its value in this way and sends 1 share to each of the 3 servers. And the servers hold an aggregator, or an accumulator, I should say, that's initialized to 0. And upon receiving these shares, the servers just accumulate them. So add them into their sort of running sum. And then the client can go offline. So it's sort of one shot from the client to server interaction. And every client does this in turn. So it splits its value into shares, sends 1 share to each of the servers, and then the servers aggregate these values that are coming from the clients. So at the end of the day, the servers can sort of add up all the shares from all the different clients they see. They publish their sort of accumulator values. And if you sort of follow this through on pen and paper, you can see that all the randomness cancels out, and the servers are left with sort of the sum of the client's values and nothing else. Okay, so the servers learn, say, that there's 3 phones on the Bay Bridge, but they don't know which 3. So this sort of simple system already gets us much of the way there. It's exactly correct in the sense that if everybody does the right thing, you get the right answer. It's private in the sense that if there's at least 1 honest server, no one learns anything except the sum of the xi's. And it's very simple to implement and requires sort of no heavy crypto. The problem is that it doesn't satisfy robustness in the way that we would like. So let me explain that. You can imagine x here is supposed to be a 0, 1 value, right? It's supposed to be 1 if you're on the Bay Bridge or 0 if you're not. What happens is that if a client is malicious and doesn't sort of follow the rules of the protocol, it can send a sharing of a large value or a negative value or a random value. And when the servers sort of receive these shares, they'll have no idea whether these shares are shares of a sort of well-formed value or shares of an ill-formed value. So I guess going back to Mayank's example of aggregating salaries, if one of the companies that's sending shares of a salary, I guess one of the cells in the spreadsheet, sends garbage, it will corrupt the whole sum that you're computing, and you'll have no idea which of the companies did it. So if you don't defend against this, you're sort of at risk of 1 bad phone screwing up your computation. And so making this sort of particularly bad in this setting is that you don't know which phone it was. And in many cases, users actually have incentives to cheat. So if you're using this to sort of privately measure ad clicks or traffic congestion or lots of things, there's incentives for users to increase or decrease the sum in a sort of malicious way. And the typical defenses, as I mentioned, non-interactive zero-knowledge proofs that I'll mention in a second are pretty costly in terms of computation. Any questions about that before I go on? All right. Cool. So let me just sort of sketch how we can protect against malicious clients using this new technique that we have. So the way we use this technique, I'll just sketch how we use it and then explain how it works. So the system works very much the same as before. The client splits its value into shares and sends 1 share to each server. But now, before the servers aggregate these values, they want to somehow check that these shares that they're looking at sum to either 0 or 1, right? That these shares are sort of shares of a well-formed data value. So more generally, you can think of the servers as holding shares of a private value x. They hold some public predicate that I'll call valid to test whether x is sort of a valid input or not, which is expressed as an arithmetic circuit. And the servers want to check whether valid of x holds without learning anything else about x. So again, in this example, valid of x is either x is in the 0, 1 range, but it could be some more complicated predicate, say on if x is a vector or whatever. So the way this works is the client, in addition, in our system, in addition to sending a share of x, it sends a share of a proof to each of the servers. And using this proof and their share of x, the servers can gossip amongst themselves and will conclude either that x is well-formed, in which case they'll accept the client's request and sort of aggregate it into the running sum, or they'll conclude that x is ill-formed, in which case they'll just reject the client's request and move on to the next client. So the point is that the servers can detect and reject malformed client submissions before they have a chance to sort of corrupt the computation that's going on. So what we need, how we implement this, I guess the way I think about it is sort of like an interactive proof system. So it's a different type of proof system, but it's similar to many others that come up in crypto. So we have a prover here that has a valid x. It is trying to convince these servers, which you can think of as verifiers, that x is actually valid. So usually in a proof system, you have one prover and one verifier, or many provers and one verifier. Here we have one prover and many verifiers. So it's a slightly different setting than you usually see. And in addition, the prover is going to send potentially a different proof to each of the verifiers. And the verifiers are basically wanting to check that valid of x holds, or in other terms, you can think of x as being in some language. That's what the verifiers are checking. So the normal properties of a proof system that we want to hold, we also want to hold here. So we have a notion of completeness in the sense that an honest phone or an honest prover should convince honest verifiers. So servers should accept a well-formed request. It should be sound in the sense that a malicious phone shouldn't be able to cheat the servers into accepting its request very often. And there's a sort of zero-knowledge property or a privacy property that if at least one of the servers is honest, the remaining servers learn nothing, no matter how they deviate from the protocol. So this is just, at least for me, sort of a nice way to look at what's going on here. If you don't know what a proof system is, you can just ignore what I just said. So there's a bunch of ways. Adam, you look really confused. Now I'm worried. No? OK. I don't want to trouble you this early in the morning. OK, so there's a bunch of ways you can implement this sort of thing. You can implement it with sort of traditional non-interactive proofs. You can implement it with fancier non-interactive proofs. Even MPC gives you one way to implement this sort of proof system I just described. And in our setting, as far as I can tell, what we've done is sort of a much more efficient solution. And I'll make that statement a little bit more quantitative in a second. But let me just sketch, again, this is going to be a very high-level sketch of how these SNP proofs work. So the setting, again, is we have these three servers. Each server holds a share of x. And they want to check that x, if they added up their shares, the sum would satisfy some predicate. So one way they could do this is run sort of a general-purpose multi-party computation to check that this predicate holds on their shares of x. So that would be one way to do this. But the downside is that these MPC protocols require a ton of communication over many rounds of communication. So the sort of communication grows with the depth of the circuit in a bad way, and also tends to require public key crypto. So instead what we do is observe that the client doesn't just know the shares of x. The client actually knows all of x. And the client can help the servers basically check its own work. So at a high level, the idea is we have the client sort of imagine in its head running a multi-party computation between the three servers. So the client just sort of thinks, what would the servers see if they ran a multi-party computation amongst themselves to check that x is valid? And the client sort of writes down the transcript of the multi-party computation that the servers would have generated if they ran a multi-party computation to check that x is valid. And then the client sends each server's transcript to its respective server. So the client sort of sends server A the transcript of what server A would have observed. It sends server B the transcript of what server B would have observed, and so on. And these are, so now the server's task is basically just to check that these transcripts are sort of valid and consistent with each other. So now the whole, Yeah, so I should say these transcripts are essentially the proofs that the client's sending. And it turns out that checking a transcript is much easier than generating a transcript. So checking that an MPC was done correctly in some sense is easier than actually doing the MPC. Right? So the client has basically given the servers all the answers. Now they just need to check that the answers were computed correctly. And again, I'm not going to go into this how this works exactly, but they sort of you can think of it as taking a randomized digest of the transcript, and this randomized digest sort of satisfies this relationship if x is valid, and it satisfies some other relationship if x is invalid. And now the servers just need to use a very, very lightweight MPC to check that this relationship holds or doesn't hold. So we've sort of reduced a big computation to a very small computation with the help of a client. And I'm gonna, yeah?
Does it, you still, if the underlying MPC protocol uses public key crypto, then the client is still running the, can you kind of get rid of the public key crypto part?
Yes, yeah. So there's another step that I'm not going to talk about, but basically the public key crypto in sort of regular MPC protocols come from generating the work goes into generating correlated randomness between the servers, or so-called beaver triples. And in this setting, the client can actually generate the beaver triples for the servers. So the client can basically do all that work. And we show that even if the client sort of cheats and generates beaver triples incorrectly, the servers will still catch the client. So there's sort of an extra trick that you need. But yeah, so the nice thing is that basically this requires one multiplication only. So it's like one beaver triple, shares of a beaver triple the client generates. And it turns out to be super, super fast. Yeah, good question. Cool. So I'm going to blow through this just so that we can get to coffee faster. But basically, there's a bunch of other ways you can do this. The slowdown that you see from doing the other ways is on the order of like 2 to 4 orders of magnitude. So the place where we still sort of suffer is the client-to-server communication grows with the size of the multiplication, or the size of the valid circuit. But it turns out for sort of special cases that are interesting in practice, you can even eliminate this cost. So again, no public key crypto, and sort of the server-to-server communication is very cheap in this system. Again, I'm not going to talk about this, but if you have a system for computing private sums, there's lots of other things you can compute. So I'll just state that as a fact. Yeah, let me skip the evaluation result for the most part. The high order bit is that again, it's like a 2 to 4 order of magnitude speed up over sort of what you would have done before, and we're within something like 10x of no privacy whatsoever. And this is a deployment like real code running on 5 servers around the world. The point is, like, you still pay something for privacy, but you don't pay that much. OK, so the last thing I wanted to say is sort of what we heard from people in industry when talking about how realistic it would be to deploy this sort of thing in practice. So there's some things that were the same in different companies around sort of Silicon Valley, and some things that were different. So the things that we heard from everyone are that sort of server resources are super cheap relative to client resources. So if you're designing a system like this, and you're able to sort of trade client cost for server cost, pushing the work onto the server always makes sense, which is sort of intuitive. The other thing that is intuitive, I guess, if you're a practitioner, but maybe not if you're more of a theorist, is that the bandwidth usage between the client and server is really, really the expensive resource, because people are using phones and they don't want to be paying, sending a megabyte of data just for the sake of your privacy-preserving protocol that needs it. Every company we spoke to that's actually deployed this sort of stuff has some story for how to defend against faulty or disruptive clients. Sometimes the story is more or less compelling, or more or less based on crypto versus other things. But everyone that we've talked to is doing something about faulty clients. So this is a real problem. The other thing, if you're interested in doing research in this area, sort of the application of these ideas that everyone was interested in is privately collecting popular URLs. So if you're a browser vendor, you'd really like to know which are the popular URLs that your users are visiting, so that you can tune your browser to be really efficient, really performant on those URLs. But URLs are like the most sensitive information about your users that you really don't want to collect in the clear. And I think sort of existing solutions for this, it seems, are sort of OK, but not great. So if you have a better story about that, I think it would be very interesting to people in industry. The places where people really, really disagreed are whether this notion of non-colluding servers is realistic or realizable in practice. People have very strong opinions, and they're very different. The second place of disagreement is whether SGX, I won't explain what it is, but it's sort of some new Intel instructions for doing sort of hardware protection, hardware security. Does SGX sort of blow away the need for any cryptographic protocols at all? And again, people have super strong opinions that are totally different at different companies, even within the same company. Let me just say really quickly the non-technical real-world considerations that came up when talking to people. The one thing is, like, if we're already collecting all of your sensitive user data without privacy protections, why should we do a lot of work to deploy stuff that does protect user privacy? And I think the pitch here that we've been trying to say is, well, you can collect even more about your data, your users, that you can't collect now if you do it in a privacy-preserving way. So you can convince your lawyers to let you collect more as long as you're careful about how you do it. Another thing that comes up is, like, we don't know yet what aggregates we want to collect, and these systems sort of bind your hands, right? You have to declare up front what you want to collect. And I guess our pitch is it's sort of still possible to retain some flexibility. The last thing I'll say that came up a lot in practice is, like, we really like this. We'd like to talk to you about this more. Please sign this stack of non-disclosure agreements that will keep you from ever publishing anything ever. And we're like, OK, we'll see. I guess we can see what they say. But before we even show you the non-disclosure agreements, you have to sign a preliminary non-disclosure agreement that covers the non-disclosure agreements. This, like, actually happened. And so yeah, those companies, I don't know what you do in that. So that's that. The story is today, we give all our data to these servers in the cloud without even thinking about it. The idea of this sort of system is you sort of split your trust into pieces, and yet these servers are still able to compute the aggregate statistics that you want. So just to resume where I started, there's these 4 properties, arguably not quite the right abstraction, but in any event, exact correctness, privacy, robustness, and efficiency. And we get them using these 2 new techniques. So thanks. Happy to take any questions. Yeah.
Got time for some questions for Henry? Yeah, Brent.
So you're saying that the primary goal is to minimize client-to-server bandwidth.
Yeah.
But basically, using MPC in the head to do signatures, to do zero knowledge, right, is more bandwidth than having them execute the servers execute the protocol by themselves.
Totally.
So I agree that it reduces computation, but it's now trading server computation for client-to-server bandwidth.
Yep. Yeah, absolutely. So I think the key there is in the actual, for the actual circuits that we care about, like testing whether X is 0, 1 or 0, 1, 2, 3, the circuit is so small that the bandwidth overhead is like a factor of 2.
So testing something 0, 1 is quadratic,
Yeah.
right? But testing if something is less than 1 million?
Well, so there's other tricks.
Circuit, right?
Yeah, there's other tricks. So if you look in the paper, you basically do the bit decomposition, and then you check whether each bit is 0, 1. And I mean, there's
But again, that's the standard thing that you would do. The servers were just executing it.
sure.
Right. I
But
guess the
problem. Go ahead.
I was going to say that it seems the big difference is that the client assists here, right? So
I agree. If the client assists, right, the MPC in the head paradigm gives you good zero knowledge, and so the client can, right, act as its own trusted dealer for the randomness, and right, but that's going to reduce the amount of server-to-server communication because they don't have to run the MPC protocol, and it reduces the server-to-server computation, but at the cost of increasing the client-to-server bandwidth, because now the client has to send the transcripts as opposed to just the secret shares. And if what you're saying is the whole goal is to minimize the client-to-server communication, it seems like this will always just uniformly increase the client-to-server communication.
Right. So I didn't say it was the whole goal. I said it was one of the goals.
Yeah.
So a couple of things. So one important thing that sort of optimization is that only the client's to 2 of the servers, the client can send a PRG key, and the last server, the client has to send a big transcript. So as the number of servers scales, the bandwidth basically doesn't increase with the number of servers. So that's in practice, that's what you do. The other thing is that to do MPC at the servers definitely is going to have less client-to-server communication, but the cost of those MPC protocols is prohibitive. It's like it's not going to happen. for the most part, because if you want to defend against malicious servers, you have to do a lot of work. Whereas this defends against malicious servers out of the box, like with no extra work. So I think if you don't care about malicious servers and your like primary worry is on the client-to-server communication, and you're willing to do a lot of server-to-server communication, which still is costly, then you would be better off using sort of MPC or potentially sort of client-assisted MPC. But I think in reality, the fact that we're able to almost eliminate the server-to-server communication and blow up the client-to-server communication by a bit and have no public key crypto is often much more attractive. Not always, but like I think in many settings would be more attractive.
Right, maybe it's relevant that the blowing up by a bit is all contingent on, say, these validity checks being simple, right? You're not checking that something's a valid English sentence or something like that. Right.
Yeah. So
there's a lot of caveats hiding in those claims.
Yeah,
right?
absolutely. I think then again, I mean, if you're checking something's a valid English sentence in an MPC, it's going to be pretty scary too. Like, you know, if your validity check is represented, has to have a huge circuit, you're sort of there's not much you can do. I mean, you can use the snark, for example, but then you have other problems.
There might be disagreements about that, but it's a good coffee conversation.
Yeah.
So let's take another quick question, then we'll go to a break.
You mentioned collecting a popular URL, existing solutions are not great. Can you elaborate?
Sure. So I guess the most prominent solution that I've heard about is the rapport system, which uses sort of local differential privacy. And what, at least in this most recent paper, you can ask the people from Google, I'm sure know much more about this than me, but I guess the accuracy, the amount of noise you have to add makes it difficult to detect URLs that aren't really popular, and also difficult if you don't know ahead of time what URLs you're interested in. So if you want to learn about a new URL that you haven't heard about, that system won't really help you so much. They have some other more recent work along those lines, but as far as I know, it's not something that sort of everyone agrees is the end of the story. Yeah, and actually the paper that's coming up at SOSP has some discussion of the limitations of rapport in that context.
Let's thank Henry again.
Yeah, thanks.